All right, today we're going to break down one of the most common, yet totally overlooked marvels of modern medicine. It's something you've probably held in your hand 1,000 times, the simple pill capsule.
I mean, look at them. We see these things everywhere, right? In our medicine cabinets, for everything from a headache to our daily vitamins. They're just there. But beneath that smooth, colorful shell, there's a whole story of incredible precision engineering and some pretty cool natural chemistry. And that's really the big question we're diving into today. We are going to peel back the layers and show you the surprisingly complex science hiding inside this everyday object. So to get started, you should know that not all capsules are created equal. They basically fall into two main families, and each one has its own unique design. Okay, so on the left, you've got the classic hard shell capsule. You know this one. It's the two-piece design with a longer body and a slightly wider cap that just fits perfectly over it. Then on the right, you've got the soft gel. That one's a single sealed piece that's way more flexible. It's usually what holds liquids or kind of gooey stuff. Now, what's really fascinating is how this all breaks down in the market. While you definitely see soft gels for things like vitamin E, the two-piece hard capsule is the undisputed king. I mean, look at that. It makes up a massive 75% of the entire gelatin capsule market. So for that reason, that's what we're going to focus on.
All right, so we've got the shell, but what is that shell actually made of? This, my friends, is where we get to the big aha moment.
The secret ingredient is gelatin. You've heard of it, of course. It's a natural polymer, which is really just a fancy way of saying it's a big molecule made of repeating parts. And crucially, it comes from collagen, which is a protein found in animal connective tissues. This chart here shows you exactly where that collagen comes from. Gelatin is made through this really careful process called hydrolysis, which basically means using water to break down collagen from sources like animal bones and skins. From there, it gets purified, filtered, and dried into the raw material for our capsules.
So why go through all that trouble just for gelatin? Well, it turns out its properties are almost perfect for this job. For one, it's non-toxic. I mean, we eat it in Jell-O all the time. It also does this really clever thing where it melts at body temperature, releasing the medicine right where it needs to go. It forms a strong film, it hides bad tastes, and it even protects the medicine inside from light and oxygen. It's a true workhorse material.
But, and this is important, not all gelatin is the same. To make a perfect capsule, you have to measure a very specific property. This machine you're looking at is a texture analyzer, and it's measuring something called bloom strength.
Bloom strength is really just a simple way to talk about how firm the gel is. Just think about making Jell-O, right? You can have a really soft, wobbly gel, or you can have a much firmer one. For hard capsules, you need a high bloom strength. We're talking 200 to 250 grams to create a rigid, stable shell that isn't going to fall apart when it's being filled and handled. Okay, so we've got our high-quality gelatin. Now for the really cool part. Let's see how this liquid goop gets transformed into millions and millions of identical, perfect little capsules.
The whole manufacturing process is this highly automated, continuous dance called dip coating. It breaks down into 5 key stages. We're going to walk through them one by one: dipping, spinning, drying, stripping and trimming, and finally, joining the two halves together.
It all kicks off right here. Thousands of these polished stainless steel pins, shaped exactly like the inside of the capsule, get dipped into a warm, temperature-controlled bath of gelatin. The thickness of that liquid is absolutely critical because that's what determines how thick the capsule wall will be.
Now, as soon as the pins are lifted out of that bath, they immediately start to spin. This part is so important. That rotation uses centrifugal force to spread the gelatin film perfectly evenly over the whole pin. This makes sure the capsule walls have a totally uniform thickness, which is vital for both strength and making sure it dissolves consistently.
And this master diagram, wow, it shows you the entire assembly line in action. After the spinning, you can see the pins travel through these really long drying kilns, where super-controlled air removes all the moisture. Once they're dry, mechanical jaws gently push the shells off the pins. Then they're trimmed to the exact right length, and finally, the cap and body halves are joined together, ready to be filled. It's just amazing to watch.
So we've built the perfect little container. Now it's time to fill it up with its precious cargo, the actual medicine.
And what's so amazing is the versatility here. Hard capsules aren't just for fine powders. As you can see, they can be filled with all sorts of things: granules, tiny coated pellets for modified release drugs, little beads, or even mini tablets.
This allows for some incredibly complex and clever drug delivery formulas. Now, to get the dose exactly right every single time, manufacturers use these super high-speed filling machines. The two main types are shown here. The auger filler on the left uses a rotating screw to pour loose powder in. The dosator type on the right is a little different. It actually tams the powder into a little compressed plug or a slug, and then pops that slug into the capsule. Both are designed for just unbelievable precision.
So, we've made the shell and we've filled it. Let's wrap things up by taking a look at why this simple little design has been a powerhouse of medicine for over 150 years.
The advantages are pretty clear. For us, the patients, they're easy to swallow, and they do a masterful job of hiding any nasty tastes or smells from the drug itself. And for the drug makers, they protect sensitive ingredients from oxygen and light, and the formula is often simpler. It needs fewer extra binding agents than a compressed tablet.
I think this quote from the research really just says it all. After all this time, gelatin isn't just some old, outdated material. It's still considered an innovative ingredient with decisive advantages. That's what keeps it so relevant, even in today's cutting-edge pharmaceuticals.
But of course, technology never stands still. While gelatin is still the gold standard, there are now modern alternatives made from plant-based materials, like HPMC or starch. These were developed to meet the needs of vegetarians or people with religious dietary restrictions, which just goes to show how this incredible technology continues to evolve.
So the next time you hold one of these tiny capsules in your hand, you'll know about the incredible science that's packed inside that simple shell. Which of course leaves us with one final, fascinating question. With all these new materials and technologies like 3D printing changing medicine, what will the pill of the future even look like?